Friends, welcome to the sixth part of our first module and the subject mechanics of solids. So, students, in the previous session, we have discussed how to write the matrix form of stress and all in three dimension. We have studied that part, stress tensor, and also principal stress and principal plane and all. Now we will move to strain corresponding to a stress matrix. We can also write a strain matrix and a deformation matrix also. So we will learn how to write those values in matrix form, right, in three-dimensional system. Okay, before that I have already discussed with you the concept of strain and all, right? So once more I will try to brief those concepts. Okay, suppose this is an object with a dimension delta x. Okay, so if it is strained to this, strained in axial direction or normal direction, there will be, if the increase is delta ux. Okay, suppose an increase of delta ux, then strain can be written as, since this is normal strain, epsilon x in x direction, epsilon x equal to delta ux, increase in or the change in length by initial length, original length, delta x. Okay, also we can write it as d by uh, dou u by dou ux by dou x. This is in x direction or x direction. Okay, epsilon x, this is strain in x direction. Similarly, if the same object is strained in y direction, if this length is delta y and this is strained in y direction. Okay, so if this length is nothing but if the increase in or the deformation is delta uy, then epsilon y can be written as delta uy by delta y or dou uy by dou y. So this is strain in y direction. So these are normal strain or normal axial strain. Maybe tensile, maybe compressive. Okay, so here I have shown you the tensile because it is getting extended, right? So this is tensile strain. Uh, another situation is we have this same object like this. If I am applying some shear force, sometimes the object may get deformed in this way. Okay, so this gets deformed in this way, either an angular displacement in both x and y, in xy plane, it is getting deformed. So if this angle is theta 2 or this angle is theta 1, okay, if this length is delta y and this length is delta x. Okay, so suppose this deformation is delta ux. Okay, in x direction, this deformation is delta uy in y direction. So you have already learned how to write shear strain in one dimension. In one dimension, you can write it as tan theta, right? Since we have two thetas here, it can be written as sum of both the tan thetas. Tan theta 1 plus tan theta 2. So how to write a tan theta 1? Tan theta 1 is nothing but delta uy, opposite. This is theta. So this angle is theta. Okay, I will use a red ink. So this angle is theta 1. Theta 1 is opposite side by adjacent side, right? So tan theta 1 is nothing but opposite side is delta uy by delta x. Similarly, tan theta 2 is the opposite side by adjacent side. Tan theta 2 is delta ux by delta ux by delta y. This is delta x. Okay. And now we can write gamma xy or the shear strain in xy plane. Shear strain in xy plane. Shear strain in xy plane is nothing but gamma xy is equal to tan theta 1 plus tan theta 2. Or if theta 1 and theta 2 are in radians, if theta 1 and theta 2 are some small, very small in value, then it can be approximated as theta 1 plus theta 2. Don't worry. And it can be written in the form delta uy plus delta x plus delta ux plus delta y. Or this can be written as dou uy by dou x plus dou ux by dou y. Opposite. If here it is y, here it should be x. If here it is x, here it should be y here. Okay. So dou by dou x of uy plus dou by dou y of dou by dou y ux. So this is how we write shear strain in a plane. Okay, shear strain in a plane. Now this is gamma xy. So similar, gamma xy equal to dou ux by dou y plus dou by dou x of uy. If it is in xz plane, it is dou by dou z of what will be ux plus dou by dou x of uz. If it is in yz plane, dou by dou z of uy plus dou by dou y of uz. That is how you write shear strain in different planes. Okay. I will be moving to deformation. Deformation metrics. Deformation metrics. I have to teach you the concept of deformation matrix. Suppose I have this xy, oh sorry, I'll draw the, even though the x, y, z plane, x, y, z system. So this is z, this is y, this is x, okay. Suppose the initial position of a point in an object is P is x, y, z. So this is my point. Okay. So after application of some force, this point P get deformed or it get displaced. Some kind of displacement takes place. Okay. So it gets displaced to another position called P dash, where the coordinates are some x dash plus x dash, y dash and z dash. Okay. So this displacement is nothing but displacement vector is I am naming it as u vector. So initially the position vector was r vector. Now now the position vector get displaced to some r dash vector. Okay. So students, r vector r dash vector is equal to r vector plus r vector plus u vector. So for the initial, if you add the displacement vector with the initial position vector, you will get the final position vector. So r dash vector is r vector. So r vector, okay, r vector plus u vector, you get r dash vector. So this will add, you know, the triangle of addition for vectors, right? That is what actually taking place here. Okay. So the displacement vector u can, since the u is a vector, you can have some three components. Okay. You can have some three components. U vector can be written as some let its three components be ux and uy and uz. So ux I vector plus uy j vector plus uz k vector. So where I, j and k are the unit vectors in x, y, and z direction. Okay, so u vector can be written in this form also. Okay, so students, the p is being displaced to p dash vector. What? P is being displaced to p dash vector. The vector p dash is called the displacement vector, and it is denoted by u. Okay, so the displacement vector u has components ux, uy, uz along x, y, and z respectively, and therefore u can be written as uxi plus uyj plus uz. Okay, so the displacement undergone by any position is a function of its initial coordinates. Okay, the displacement undergone by any coordinates will be is a function of its initial coordinates. So we assume the displacement is defined throughout the volume of the body. So the displacement vector, the displacement vector u of any point b p belonging to that particular body is known once its coordinates are known. Okay, if the initial coordinates are known, you should be able to calculate the you should be able to determine the displacement vector. So there we can say that then we can say that a displacement vector field has been defined throughout the volume of the body. So I will show you an example through I will show you. I will make you clear this concept through an example. Okay. Suppose students, this is a problem. A displacement field for a body is given. So the u vector in the form of uxi, uyj, uk is given. Here u equal to x square plus yi, 3 plus z x square plus 2yk. Okay, the position is given. What is the deformed position of a point originally at 3, 1, minus 2? So original position P is known. So students, uh, P is known. P is some 3, 1, minus 2. U vector is also given in the form of ux, I plus uy, j plus uz, k, right? Actually in the question it is like x square plus y, I plus 3 plus z j plus x square plus 2y k, right, x square plus y, 3 plus z and x square plus 2y. Okay, so this is given. You have to find the deformed position or p dash. What is our question? P dash equal to the unknown. P dash should be found out. Okay, so how to find out how to find out p dash? So we know the equation r dash vector equal to r vector plus u vector, right? So u vector is known. We have to make the position p vector. We have to find the r vector. How to find r vector? R vector is nothing but xi plus yj plus zk. We just put that coordinates in x, y, z is known. So r vector will be xi plus yj plus 2k. What will be? X is 3, 3i, y is how much? Y 1. So j x equal to 3, y equal to 2, sorry, y equal to 1, z equal to minus 2, right? So here minus 2, okay, right. Now since u equal to 3 square plus 1, sorry, u equal to x square plus y I plus 3 plus zj plus x square plus 2yk, right? So I am substituting here x equal to 3, y equal to 1, z equal to minus 2. Substitute, you will get u equal to some 3 square plus 1i plus 3 minus 2 j plus x square is 3 square plus 2 into 1 k. So we will get u vector as 3 square means 9 plus 1 10i plus 1j plus 9 plus 2 11 11k. Okay. Okay. So students, this is the displacement vector u vector. Sorry, these are u vectors. U vectors at the point p, at the point p, u vector at point p. This is the value 10i plus 1j plus 11k. Okay. So r dash vector will be r vector plus u vector, right? So r vector and u vector are known now. What? 3i, r vector is 3i plus j minus 2k plus u vector is 10i plus j plus 11k. So if you add all the I values, j values and 2k values separately, you will get 13i plus 2j minus plus 9k. So this is the new position vector. So p dash will be its coordinates will be 13 2 9. This will be the new coordinate for displaced point. Displaced points in new coordinate will be 13 2 9. Okay. Students, now I am taking 2 points in a body. Let P be a point in the body with the coordinates some x, y, z. Q be another body, another point with maybe coordinates x instead of x, y, z. You can take some x plus delta x, y plus delta y, z plus delta z. So when the body undergoes deformation, the points P and Q move to some new position P dash and Q dash. Okay. So this is the displacement of P. This is the displacement of Q. Okay. P is displaced to P dash, Q is displaced to Q dash. So PQ is now deformed to another. PQ is deformed to P dash Q dash. PQ is deformed to now PQ is deformed to P dash Q dash. The length PQ is deformed to P dash Q dash. Okay, so when the body undergoes deformation, the point P and Q moves to P dash and Q dash. So the displacement vector U at P have component. Okay, this is the displacement vector at P. Displacement vector at P. Okay. Now I will show you. Suppose P is a point with the coordinates x, y, z. Q is some another point with another coordinate x plus delta x, y plus delta y, z plus delta z. Okay. Suppose uh, u vector is the the displacement vector at P. At P. Suppose its coordinates is ux, uy, uz. Okay. Therefore, P dash will be what? P dash will be x plus ux, right? X plus ux and y plus uy and z plus uz. So this will be the new P dash because P dash is the displaced position of P. So since the displacement vector is ux, uy is uz, so the x will be displaced to x plus ux, y will be displaced to y plus uy, z will be displaced to z plus uz. So what will be q dash? So this is original q. This is original q. Oh, So you have to find q dash, values of q dash. How to find? So students, if u vector is the displacement vector at p, displacement vector at p, displacement vector at p, okay. Displacement vector is u at p, and its coordinates components are ux, uy, uz. Okay. Now, if the displacement components at q differ slightly from those at p, but q is very close to p, but displacement vector will be slightly different. It won't be the same. So the displacement vector at q can be approximated as u vector plus some delta u vector. This is displacement vector at q. Vector at q. Okay, so u vector is displacement vector at p, and q is another point which is very close to p, but slightly different. Not the same, but slightly different. So we can take u, the displacement vector, some u vector plus delta u. So what are the components of u vector? Ux, uy, uz, right? Therefore, u vector plus delta u vector components will be ux plus delta ux, uy plus delta uy plus uz plus delta uz. This will be the components of position vector at q, right? At q. Now I can write delta ux as dou ux by dou x into delta x. So this method of approximation, well, you might have learned in your maths class. Approximate delta ux can be written as dou ux by dou x into delta x. Or you know how to write delta. You might have say you know delta ux by delta x can be approximated as dou ux by dou x, right? Delta ux by delta x is nothing but dou ux by dou x. So if you take delta x to this side, you can get delta ux equal to dou ux by dou x delta x. So this is called a first order approximation. So the only first order approximation required. So you can similarly you can write equations for delta. So students, delta ux can be written as, actually since it is in 3 dimension, you have to write it as dou ux by dou x into delta x. That is what we are learning. But since this is in 3-dimensional problem, you have to write it as dou ux by dou y into delta y plus dou ux by dou z into delta x. So this way you have to write. Similarly, delta uy can be written as dou uy by dou x delta x plus dou uy by dou y delta y plus dou uz by dou z delta z. Similarly, dou uz can be written as dou by dou x of uz delta x plus dou by dou y of uz delta y plus dou by dou z of uz. This is uy, okay. Dou z delta z. So this is how first order approximation of delta ux, delta uy, and delta uz are written. So students, you just keep it in mind. This is how we write delta ux, delta uy, and delta uz. Okay. So what was our aim? Our aim was to find the position vector of q dash. Actually, Actually, q is nothing but x plus delta x, y plus delta y, z plus delta z, right? So our position vector at q is nothing but u vector plus delta u vector, right? Its components are ux plus delta ux, uy plus delta uy plus u and uz plus delta uz. So we can we studied how to write delta us, delta uy and delta uz, right? First order approximation. So this is how you write delta uy. These are the equations for delta uy, delta uz and delta ux. Okay, so you know how to write. Now we can write q position of q dash vector. The position of q dash is will be nothing but you add this and this, x plus delta x plus ux plus delta ux, y plus delta y plus uy plus delta uy, and third z plus delta z plus plus z uz plus delta uz. So this is the new position of q. Okay, now q got displaced to q dash. Similarly uh, p dash will be, so this is p dash is this one, x plus ux, y plus uy, z plus uz. Q dash is x plus delta x plus ux plus delta ux, y plus delta y plus uy plus delta uy, z plus delta z plus uz plus delta uz. So this is how two points p q displaced to p dash q dash. Okay. So students, these terms are very important here. Delta ux, delta uy, and delta uz, right? So you know how to write those terms. In those terms, various differential terms like dou by dou x of ux, dou by dou y of ux, dou by dou z of ux, all these terms comes, right? What all terms come? Actually, you can write it here. Here delta u will write. Here delta ux is nothing but dou by dou x of ux delta x plus dou by dou y of ux delta y plus dou by dou z of ux delta z. So students, we just note down that there are total 9 differential terms here. Note down all these 9 differential terms. Okay. Now these differential terms are very important. Before deformation, the segment PQ has had component delta x, delta y, delta z along 3 axes. After deformation, P dash Q dash has component. Okay. Uh, After our deformation, P dash Q dash has component delta x plus delta ux. Okay, such delta y plus delta uy is delta z plus delta uz along the 3 axes. So these differential terms has become important in the analysis of strain. Okay. So the differential. So if you differ delta ui by delta j, delta xj. So simply, if you write these differential terms in a matrix form, dou ux by dou x, dou y of ux again, dou by dou z of ux again, dou by dou x of uy, dou by dou y of uy, dou by dou z of uy, dou by dou x of uz, dou by dou y of uz, dou y of dou by dou z of uz. So this matrix is known as displacement gradient matrix. What? Displacement gradient matrix. Why? Because these differential terms are very important in finding the strain of that particular segment PQ. Segment PQ, right? So PQ is deformed to P dash Q dash. The PQ segment is deformed to P dash Q dash. In order to find P dash, it is okay. It can be easily found. But if you find Q dash, if you have to find Q dash, you need the value when you differential dou by dou x of ux, dou by dou y of ux, dou by dou z of u. So this matrix is very important. This matrix is very important in finding Q dash. So this matrix is therefore known as displacement gradient matrix. So these are the gradients of the displacement components at a point P in x, y, z direction. Gradients. You know how to find grade of a vector. You might have studied in your maths class. Grade, divergent, curl, and all. Right? So this is finding gradient of the matrix. So these finding this gradients of the displacement components are very important. Gradients of the displacement component x, y, and z direction. These are very important in analysis of strain. So one can represent this in the form of matrix called displacement gradient matrix. Okay. Now, students, I will be showing you how to write strain matrix in rectangular system, strain matrix in rectangular Cartesian system. So since this is Cartesian three-dimensional system, you will have 9 components, 3 by 3 matrix. It will be a 3 by 3 matrix. So you have already learned how to write the matrix form of stress. Similarly, there is also strain matrix and strain matrix. So you know how to calculate, how to define strain. I have already shown you in the first slide, right? So this is normal strain, epsilon x. Okay. So this is normal strain in y direction. Similarly, there will be a normal strain in z direction also. And there is a shear strain in xy plane. Okay, shear strain in xy plane. Similarly, there will be shear strain in yz plane. Similarly, there will be a strain in xz plane also. Right. So we can write the state of strain at a point. State of strain at a point. So we have epsilon x or epsilon xx, epsilon yy, and epsilon zz. Similarly, gamma in xy plane, gamma in yz plane, gamma in xz plane also. Right? Right? So how to write what is gamma xx? Epsilon xx is nothing but dou by dou x of ux. Similarly, gamma yy is nothing but dou by dou y of uy. Gamma z is nothing. Epsilon z is nothing but dou by dou z of uz. We have already learned in the first slides. Now how to write gamma xy? Gamma xy is nothing but theta 1 plus theta 2, or dou ux by dou y plus dou y by dou x, right? Dou u by dou x. Similarly, gamma x xz can be written as dou by dou z of ux plus dou by dou x of uz. Similarly, maybe gamma y z can be written as dou by dou z of uy plus dou by dou y of u z. So this is how we write shear strain components in xy plane, yz plane and xz plane. So students, the state of strain at a point, the state of strain at a point, state of strain, similar to state of stress at a point, we can write state of strain at a point can be determined, can be written using the strain matrix. In the 6 rectangular strain components at a point, say P, one can calculate the linear strain in any direction PQ using equation using the strain matrix. Okay, strain matrix. The totality of all linear strains in every possible direction can be defined using the state of strain at a point P. So I will write the strain matrix epsilon ij equal to, writing it is epsilon xx. Now next will be gamma xy gamma xz. Similarly, gamma xy itself here, epsilon yy gamma yz. Similarly here gamma xz gamma xy, sorry here yz gamma zz. So this will be the strain matrix. So you know how to find gamma xs, gamma baby, gamma zz. Epsilon xx, epsilon yy, epsilon zz. Gamma xy and gamma xy are same here. These two are same. These two are same. Okay. So this is how we write the strain matrix. So I will do a problem, then you will understand how to calculate strain matrix. Students, before that, these relations, this one, uh, this one, and this one are known as strain displacement relation. Strain displacement relation of Cauchy. All these relations are called strain displacement relation of Cauchy. Very important. It's all this relation, this, and all these three. These relations are called strain displacement relation of Cauchy. Okay. Now I will do an example. So students, as an example, consider the displacement field u vector is given. What are the rectangular strain components at point P? 1, P with the coordinates 1, 0, 2. Use only linear terms. Okay. So don't worry about linear terms. Now how to do this problem? You have to find the strain matrix or strain tensor. How to find? It is given, the u vector is given, right? U vector is given. U vector is nothing but y square I plus 3yz j plus 4 plus 6x square k whole into 10 raised to minus 2. Okay, so ux is nothing but y square into 10 raised to minus 2 I. Uy is nothing but 3yz into 10 raised to minus 2. Sorry, this I is not required here. Uz is nothing but 4 plus 6x square whole raised to 10 raised to minus 2. So 10 raised to minus 2 is constant, so don't worry about that constant. So So these are the values of components of ux, uy, and uz. Right now, what we need to find? We need to find the stress matrix. What all things? We have to find sigma xx, sigma yy, sigma zz, gamma xy, gamma yz, gamma xz. These six components should be found out. Right? Right. So how to find gamma xx or sigma xx first? Sigma xx is nothing but dou by dou x of ux. So what is ux? Or dou by dou x of means dou by dou x of ux is nothing but y square into 10 raised to minus 2, right. So this is since this is with respect to x, this term has no x, so this will be 0 because here no x is there. So it is considered whole as constant, so it will become 0. Similarly, sigma yy equal to dou by dou y of 3yz, right? 3yz into 10 raised to minus 2. So it will be, since y is there, we can write it as 3z into 10 raised to minus 2, right? Similarly, sigma zz will be dou by dou z of what 4 plus 6x square, 4 plus 6s square into 10 raised to minus 2. Since there is no z terms, it will be 0. Okay. Now we have to find dou by dou ux by dou y. That is dou by dou y of y square into 10 raised to minus 2. So you try to do all these things here on. I will just write the answer. Answer will be 2y into 10 raised to minus 2. Okay. Similarly, dou uy by dou x is nothing but it will be 0 because there is no terms of x in uy. Similarly, dou uz by dou x is nothing but you will get 12x into 10 raised to minus 2. Just check it. Okay, just check it. Now dou by dou z of ux equal to will be 0. Dou by dou uy dou z will be some 3y into 10 square 10 raised to minus 2, right. So actually we found all the differential terms. Now you can write gamma xy will be dou ux by dou y plus dou by dou x of uy, right. Since these two values are 0, you will get gamma xy equal to 0. Similarly, gamma yz equal to dou uy by dou z plus dou by dou y of uz. It will again be 0, right. So before that, I will write all the terms once more. I will write all the terms once more. Wait. Dou ux by dou x equal to 0. Dou uy by dou x equal to 0. Dou ux equal to 12. Dou ux uz equal to some 12x into 10 raised to minus 2. Similarly, dou y of ux equal to 2y into 10 raised to minus 2. Dou uy by dou y equal to some 3z into 10 raised to minus 2. Dou uy by dou z equal to 0. Dou ux by dou z equal to 0. Dou uy by dou z equal to some 3y into 10 raised to minus 2. Dou uz by dou z equal to 0. Okay, so you have values for this much values. Okay, in this values you substitute the value of you have to find linear strain at value of p, right? Value of point p. Linear strain at p should be found out. So the coordinates of p is 1 0 1 0 2, right? So here for y, z and x and all y, here all you substitute the value of coordinates of p. Okay, so coordinates of p you will get since x equal to 1 you will get this value as, here it is 4 what's the value here, 12x, right? 12x into 10 raised to minus 2. Since x is 1, you will get the value of some 12 into 10 raised to minus 2. 12 into 10 raised to minus 2. X is 1. Here y, since y equal to 0, our point is 1 0 2, right? Y is 0, so this will be 0. Z is 2. Z is 2, right? So here you will get 6 into 10 raised to minus 2. This is 0. Here y is 0, so there will be 0. So these are the values. Okay. Now you will get gamma xy equal to dou ux by dou y plus dou uy by dou x, right? So this will be 0. So gamma yz equal to dou uy by, actually 0 plus 0 will give you 0. Dou uy by dou z plus dou by dou y of dou uz. So this will also be 0, since this value and this value is 0. And gamma xz will not be 0. Ux plus uz dou by dou x of uz will be 0 plus some 12 into 10 raised to minus 2. This value will be 12 into 10 raised to minus 2. Okay. Now sigma xx will be what? Dou ux by dou x itself. So its value is 0. Sigma yy will be dou uy by dou y. Its value will be some 6 into 10 raised to minus 2, right? So you get, I think, your dou uy by dou y equals 6 into 10 raised to minus 2. Similarly, sigma epsilon z equal to dou by dou z of uz, and this value is also equal to 0. So this is how you find the strain matrix. So you can write this in the form of strain matrix. Okay. Strain matrix will be, you can have a strain matrix. Sigma epsilon xx is 0. Epsilon yy is 6 into 10 raised to minus 2 at point P. Yes, this is 0. xy is 0. This is 0. xz is 0. These two are 0, and this is not. Sorry, xz is not 0. This 12 into 10 raised to minus 2. This is also 12 into 10 raised to minus 2. These two are 0. So this is the strain matrix for the given question. Thank you.